Cool. Okay, so in the next couple of talks, we're going to be talking about the cut operation. And I guess as it relates to what we've already been talking about with composition in LG. So as always, let K be a commutative ring. And consider the following morphisms in LG. So these are all potentials. So we're going to need to specify the number of variables in the ring K y. So let Ky be this polynomial ring in n variables. And JV be the Jacobi ring of the potential V. So that's the ring Ky modded out by the partial derivatives V n, right, 1 here of V. Okay, and so definition, we'll define the cut. I should get this, sorry, we'll call this morphism X and this morphism Y. The cut of the morphisms above is the matrix factorization y bar x, where y bar x, the module, is x tensor over ky with the Jacobi ring and y, and the differential is just the sum, is just the sum of the two differentials of x and y. So in previous talks, the cut arose in the proof last week that composition in LG is well defined, specifically when showing that x tensor y, so this matrix factorization I'm writing down now, is the direct summand of a finite rank matrix factorization. So if we take a look on the second board, the main idea of this proof was to show that we had a strong deformation retract between the cut. We didn't call it the cut then, but it was. And this stuff on the left-hand side, which has the relevant matrix factorization as a direct summand. With the usual, with the differential of x tensor y there. And we showed that the cut is finite rank, and the module on the left-hand side, well, that has is just a direct sum of copies of x tensor y, some of which shifted in degree. And the goal of this next part of this seminar is to better understand how x tensor ky, how this matrix factorization sits inside this thing. Okay, so to review how we found this strong deformation retract, well, we took the following steps. So we started out with a strong deformation retract, like so. We began with a strong deformation retract from the Jacobi ring to the causal complex of the sequence of partial derivatives. We then used perturbation to introduce the differential of x tensor y. And then we showed there was isomorphism. There was an isomorphism which removed the causal differential. And in this talk, and probably the next couple of talks, we're going to focus on the first one here. We're going to understand the formulas for this strong deformation retract here. So we'll get on to doing that. Okay, so let's take a look at the third board now. So the key idea in constructing this strong deformation retract, so from now on, I'll just call this the strong deformation retract. So the strong deformation retract between the causal complex and its and the Jacobi ring. So the key idea in constructing this strong deformation retract is a generalizer. Oh, yeah, sure thing. Oh, yeah. So the key idea is a generalization of the usual partial derivative maps. So so generalizing these partial derivative maps on ky. And we're going to sort of, I guess, specify what we mean by that as follows with the following definition. So let R be a K algebra. So really R is ky. At least it will be in this talk. And T a sequence of elements in R. Let KT, a subset of R, be the K algebra generated by 1 and the elements of the sequence T. So this is just polynomials in these polynomials T over K. So we're going to call a system of T derivatives are K linear maps, one for each of the TIs from R to itself, which satisfy the following. So 1, every F in R can be written uniquely in the form F equals to U of T to the U. So by T to the U, I mean, so U is a vector of natural numbers of length n, and by T to the U, I mean T1 to the U1 times T2 to the U2 all the way up to T n to the UN. Uniquely in this form where RU belongs to the kernel of all of these maps. Then I guess we'll go over to the second board. The second property is that for F in this KT algebra, and are in the kernel of all these ti, del ti, we have that we can factor out this r. And then lastly, that the derivative, I guess this map applied to TV, right, is equal to VI T VEI, where V is in N, N to the N, and EI is a whole bunch of zeros with a 1 in the ith position. And here we understand that 0 times tj to the -1 is 0, right? Just to sort of save on space. If you had a look at the notes before this talk, there was a fourth condition here as well. That fourth condition follows from these three, so I won't mention it here. Okay, so in a future talk, we're going to show how to construct a system of t derivatives when t is a quasi-regular sequence. So either when, in two cases, so either when r is just ky and k is a field, or when r is the completion of the polynomial ring of ky. So this is the t-adic k any commutative ring. But we'll save that for a future talk. And for this talk, we're going to focus on the case in which k is a field. So we don't need to think about the completion for the time being. Are there any questions before I continue?
Are you able to say why you're generalizing this notion? It seems like the partial derivative is the salient example of this. I'm trying to generalize it out to quasi-regular sequences or something, clearly.
Yeah. So I guess I came up with this list of properties because they're exactly the properties that we need for what I'm about to say to work. I guess when you so you're right? Like when this sequence ti is just y1 through yn, then the regular partial derivative maps, like the normal partial derivative maps, do form a system of t derivatives. And if you go through this, so in the case of LG, that corresponds to v being the sum of squares of each of the variables. You can do that, but I guess this generalizes to any potential in LG. Does that exactly answer your question, or maybe not?
Yeah, I'm probably just need to see the rest of the talk. I'm just
okay.
Or maybe do you have like a easy example of where you want a system of t derivatives where those t derivatives aren't the regular partial derivatives? Like, where do you need this generalization?
So we're going to need it for constructing the cut whenever v is not. Taking a look at this board. So if v is not, say, this potential. So we need a system of t derivatives for t equal to the partial derivatives. Oops, sorry, this should be 1. right? Because we're going to be constructing a system, also we're going to be using a system of t derivatives where t is the sequence of partial derivatives, and when that sequence of partial derivatives does not give you the variables in the polynomial ring, we need a generalization of that.
Yeah, okay. All right, that's helpful.
Rohan's about to explain how the strong deformation retract in part 1 over there is built. I mean, the explicit formula for it is built out of this system of t derivatives.
Oh no, hang on one sec. My iPad has disconnected from... Give us 2 seconds, sorry about that.
While we're waiting for that, I'll comment. I'm here with 2 characters, and one of them is in VR. So I'm sitting here with my headset on, watching your talk. It's actually pretty cool.
Yeah, cool.
So I can just turn my head and see all the boards. That's really, really useful.
Yeah, nice. Oh, what is going on? It just disconnected again. Look at that.
It's disconnecting from Roblox.
Okay, sorry about this. No, I've been using a slightly different way of connecting my iPad so I can use the computer and Roblox at the same time, and it's worked in every previous talk, and now it's falling over. So it's okay. Fingers crossed. All right, let's continue. Back over on the first boards. Okay, is that all for me? Yep. Okay, so for now we focus on the case in which K is a field, and consider the potential Ky with V, which I just erased. So that was the middle potential in our 3 morphisms, which we're constructing the cut for. And let T be the sequence of partial derivatives, y1 v through yn of v. And suppose we have a system of t derivatives. So again, we will construct these explicitly in a future talk. So yeah, and that's because since V is a potential, T is quasi-regular. So later on, we'll see how to construct these maps. Next, consider the causal complex. Kt dk of the sequence of partial derivatives. And we denote the module of the causal complex as follows. As the exterior algebra of this thing. And here, the dt1 through dtn are just formal generators. So there's no, I guess, technical difference between denoting the causal complex like this and any other way. But this is to sort of emphasize the analogy with what we're going to do with differential geometry. So the idea is to think of the degree p part of the causal complex, or rather this module, as being a module of p forms on affine n space. We call the degree 1 part, I think, is usually called the module of Kähler differentials. I'm going to remind you of the differential on the causal complex. So that is dk is this dt oops, sorry, dt I I star, where this thing here is contraction. Okay. Definition. Not in that color. So given a system of t derivatives, so we define the corresponding connection as a k-linear map from the module of the causal complex to itself, given as follows. So applied to a arbitrary element, so f being a polynomial in k, in ky, and this is multiplied by some basis vector I1, Ti1 through Tip, right? So this thing lives in the degree p part of the causal complex. This thing is the t derivative of f.
Looks kind of like you've written commas and dots there, but you don't really need commas, do you?
Additional, this should probably be a j just to make this easier to read. So the jth t derivative of f multiplied by the generator dtj with the original stuff here as well. Ti1 through Tip. This is I equals 1 to n. Okay. So if you've been looking at the cut paper, which I guess this talk is really based on, this is the same connection that appears there. And in that case, first the connection was proved to exist, and then the maps ddti were extracted from that connection, whereas here we're constructing the connection from the maps. Except I haven't told you how to construct the maps yet, but I guess that's the approach we're taking. Any questions so far?
What's the word before connection in the definition? So given dt1 up to dt, we define the... Oh, okay.
Yeah.
Yeah, so you just define the connection. Yeah, that's fine.
Yeah.
Nice. Thanks.
Okay, cool. Okay, so now we're going to just prove some stuff about this. First one is to show that this connection squared is 0. So I guess first note that properties 1, 2, and 3 of the system of t derivatives together imply that the system of t derivatives maps commute. For all I and j, and then we just compute this thing squared, right? So for some arbitrary element that I'm going to apply this to, we have dti1 through dtip. Okay, well that is the sum of this thing from I bet he is j of del tj of f d tj dti1 dtip. Okay. And then we do the same thing again. So we get, well, I guess I'm going to have to use I here. So that is the second order derivative. Okay, and then we can just split this sum up into two parts. So for I less than j, we have dti dt j of f dti dtj okay, and then we get the other part, j less than I. Okay, dt I dt j of f dt I dt j dt I1 p. And then we can just change variables in the second part, right? So, well, first of all, we can swap these two things around because these maps commute, and then we can swap, whoops, these two around and introduce a negative sign because that's how the wedge product works. And then we note that these two things are just equal to each other, where we swap I and j in the sum, which I won't do because I'll probably miss an I or a j. But all this thing comes out to is 0, right? So that proves that lemma. In the terminology of the cut paper and the some of the other papers, what we've shown here is that the connection is flat. But I won't use that terminology. Okay. I better leave up the definition of the system of t derivatives because I'll probably keep referring to it. So we'll go back to the first board. Okay, so next we have another lemma. So if Q, so the rational numbers are contained in our field K, so I guess if K is a field of characteristic 0, then dk, so the derivative of the causal complex, and the derivative, and the connection applied to this algebra KT, then the image of that thing just comes out to be the ideal generated by the ti through tn. Okay, so again, this is just a matter of computing it. So dk and nabla applied to tu. So I guess tu is t1 u1 through tn un. U is something like that. Okay, well that thing is the sum from j equals 1 to n of of dk applied to uj. So here I'm applying the t derivative to this thing using property, I think I listed it as 3. Oops. From that system of t derivative stuff, dtj here. So here this thing is the same thing, right? This ej is just the jth basis vector in I guess Zn. Standard basis vector. Okay. And then we apply that as well. So j equals 1, and n. And here we get uj coming along, ti, tu equals minus ej, and we get t d t I, yeah, yep. And the contraction of that applied to d t j, right? But now, well, this thing is just the Kronecker delta of I and j. So all of this comes out to the sum of the uj multiplied by tu, right? And I guess here we're sort of implicitly saying it's okay to write 0 times tj to the minus 1. We say that is 0. I guess to avoid just treating that case separately. Okay, so this shows that dk of nabla of kt, so by extending linearly, because both of these are k-linear, that is a subset of T1 through Tn. But it also shows that for any Tu in, this is not well written, for any Tu in T1 through Tn. So another way to say that is just that at least one of the Ui is not 0. That this thing is equal to dk nabla of the sum of the Ui inverted, right? So this is where the hypothesis that Q is a subset or a field is characteristic 0, and multiplied by Tu, right? So that gives us, and we can invert that because at least one of the uj is non-zero, and then that completes the proof of this lemma. Okay. If there's no questions, I'll continue on the second board. Okay, so again, we have more lemmas to prove. I should say as well, so I think, if I'm not misunderstanding, then in the terminology of the cut paper and the pushing forward paper, this shows that the connection nabla is standard. But again, I won't really use that terminology. Okay, on to another lemma. Okay, so the next thing to show is that decay, so the graded commutator, oops. So that thing is just decay nabla plus nabla decay is a morphism of complexes, right? So it commutes with the causal differential, right? So proof, well, I guess first we note that this thing actually has degree 0, right? And then we have that dk nabla composed with dk. Well, that is dk nabla dk plus nabla dk squared. This thing is 0. So we can also write 0 as dk nabla dk, oops, plus dk squared nabla, which is the other thing, right? Okay. Great. Okay, so we continue proving stuff. Lemma. Okay, so for this one, if Q is contained in K, so if K is a field of characteristic 0, then this commutator is invertible away from degree 0. Okay, so by that I mean each component of this map, except for the degree 0 component, is an isomorphism of modules. Okay, so let's do that. Let TU dt1, so TI1 through TDTIP and KT for P greater than 0. So this thing lives outside of the degree 0 part. And I guess here we're assuming that I1 through IP is a strictly ascending sequence. Okay, and then we're going to define something just for our convenience here. So let delta J be 0 if J is contained in, is one of the I1 through IP, and 1 otherwise. So I guess it's like sort of the opposite of the characteristic function of this set. Okay, and then back to the first board. Okay, and then we compute. So dk of nabla. So we'll do each part individually. Note what we end up with is invertible when we add them together. So applying this part, we get du dt1 di1 dtip. Okay, so sorry, I'm doing the other calculation first. I want to stick to my notes. Okay, well, so that is the sum from L equals 1 to P of -1 to the L plus 1 of nabla applied to T I L TU D TI1 emitting TIL IP, right? So we skip the hatted factor in that product. Okay, and then that thing, again, we just apply nabla. L equals 1, J equals 1. So that is, I guess this thing is TJ applied to TIL TU DT J DTI dti1 dti p. Yep, except I guess need to remember that we're skipping TIL. No need for that. Okay, and hold on, what on earth am I doing here? Okay, no, sorry, that's looking okay. Okay, so that comes out as, so we'll split the sum up into two parts. So we'll sum from L equals 1 to P from, well, we get L plus 1, U, I, L plus 1, TU, right? So this is where U is equal to, sorry, when J is equal to IL, right? And here we get DTIL, whoops. I1 TIL. Okay, and then the other stuff is over here. So this is going to be a sum over J and L in some set A, which I will specify. And that is going to be delta J minus 1 to the L plus 1 U J T U minus EJ minus, plus AIL DTJ DTI1 DTIL emitted. Okay, I need to tell you what A is. So A is the set of pairs J and L such that J is equal from, well, it's all things from 1 to N. L runs from 1 to P. And J is not equal to IL. Okay. All good so far, I think. And then why do we get that? Oh, right. Okay. And then we can rewrite this first sum as we can get rid of this thing, right? So the idea is we're moving this thing. Whoops, sorry. This thing back into position, right? So we can get rid of this. Whoops. Put that back into position and cancel out that minus sign. And then to do that, we also need to introduce this factor of 1 minus delta j, and so delta j being so 1 minus delta j will be 0 if j does not belong to this set. Why is that? Yeah. Oh, okay. Okay. I guess. Sorry. So if in my notes, what I've written is the sum. This should be a sum over j here, right? From j equals 1 to n, and I guess the reason I wrote it like that in my notes is because it matches up more easily with the next calculation that we will do. Okay. So yeah, I guess this is just deleting the terms that don't exist in this sum. Yeah. Okay. I guess we continue. So now we need to compute the other part of this sum. The idea is that this horrible big complicated thing at the end is just going to cancel, right? Okay. So the sum over the elements of the set A. Okay. So next we compute decay of nabla of the same thing. So that is the sum of j equals 1 to n dk uj d u minus e j t j dt I1 dt IP. Okay. Here that we get that this term is 0 if j already exists in is already an element of the ti1 through tin, and then we get this thing coming out. So uj, the sum of uj, I guess I'm using s now, n of t u minus ej, and then contraction by s, ts, dts. Sorry for breaking this product up. But that is, well, that's just that thing. Okay, I'll give myself some more space. Okay, and that is the sum. So again, we just split this sum up to get delta j uj tu d t dt I1 through dt IP, right? Plus the sum from j and L in A, in our set A, delta j here again, minus 1 to the L this time because there's an extra term in the product, the product of dti's at the end, tu minus e j plus eil dt j dt I1 dt ip removed. So I guess the first one corresponds to where we're deleting the first thing. Okay, and then I guess we just observe, right, that, well, this big horrible thing at the end here is the negation, because of the different power of -1 here, of the big horrible sum over a that we just computed. So when we compute the sum of these two parts, we get that decay of nabla applied to, oops, tu dt1 ti1 tip, that is just some constant times tu dti1 through dti p, where c is this thing, is the sum of j equals 1 to n of 1 minus delta j plus uj. And c, whoops, that's a bit strange. And c is not 0 since delta j equals 0 for some j, right? Because there's at least one of the dti dtij that are in this sum. Okay, and then we can extend, I guess, sort of some semi-linearly using properties 1 and 3 of, 1 and 2, I think, as I wrote it up there, of the definition of the delta ij maps, to show that this thing is then invertible for all elements in ky.